again, everybody. This is Luboš Pirkl from CFD Support. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal fan from scratch in CFturbo, and then how to simulate it and evaluate it in TCFD. The webinar is being recorded, and its recording will be made available on our YouTube channel. I hope all the techniques works just fine now. And in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. Okay, so please let me introduce the speakers of today's webinar. So this is me. My name is Luboš Pirkl. I am co-founder of CFD Support, and my current position at CFD Support is telling the world what we do. I'm gonna guide you through this webinar today. I'm here in our Prague office with my colleague Radek Máca. Hello, Radek.
Hello, Luboš, and hello to everybody who is watching us.
Okay, so Radek, are you ready for the webinar?
Yes, I am.
Okay, and finally, together with us on the line, there is Oliver Felde from CFturbo in Dresden. Hello, Oliver.
Hello, Luboš, and hello, everybody.
The same question, how are you today, and are you ready for the webinar?
I'm fine, and I'm ready. Thank you.
That's great. I will only note that Oliver is Senior Manager CAE at CFturbo, and he is responsible for consultancy and software development, especially for the implementation of turbomachinery design theory and related algorithms in CFturbo software. Here's the schedule of today's webinar. So the webinar is going to take about 1 hour, depending on number of your questions and comments. There will be 4 parts in this webinar. In the first part, there will be this general introduction. In the second part, there will be, we can call it the design part or CFturbo part. There will be a live example where Oliver is going to introduce CFturbo a little bit, and then he will show us a live example of centrifugal fan design from scratch in CFturbo software with a final export of the designed model to for TCFD. In the next part, let's call it the simulation part, there will be another live example where Radek is going to show you the TCFD simulation of that centrifugal fan exported by Oliver from CFturbo in the previous part. And finally, there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions. All the questions will be answered. Some of them will be picked and answered right in this webinar. The rest will be answered via email later after the webinar is finished. So this is quite important. So feel free to put your questions, and it's your time. Just take your chance, and we will gladly answer all your questions. Okay, so I think we can slowly start. So let's move to the design part of the webinar. I'm gonna hand over the presentation to Oliver. So Oliver, are you ready to tell us about CFturbo?
Yes, I'm ready. Yeah, okay. CFturbo is a German-based company with offices in Dresden and Munich. We produce our main product, that is a special CAD software called CFturbo, and that is a modern and powerful software tool for the design of turbo machinery and all its components. And we call it conceptual design because it starts with a design point rather than with geometric information. Right now, we have something like 200 active clients globally, and we offer CFturbo, which can be used with different models that have been implemented to design pumps, both radial as well as axial, fans and blowers, again radial and axial, compressors, turbines, and of course the other components which are necessary to complete the stage, which are stators and diffusers, plus the volutes. And with our software, we serve the following industries, and amongst them there are aerospace, automotive, consumer products, energy, oil, gas, marine, mechanic, process engineering, and also the semiconductor industry, because there you find a lot of fans that are used to cool down, for instance, CPUs and so on. Okay, what I want to show you today is a live example or a demo example of a design of a centrifugal fan. And when you can see my desktop, I'm going to start with really from scratch with defining an operating point. But first I have to choose which kind of machine I want to design. And of course, it's going to be a ventilator, a fan. As I said before, the central entry into the software is the definition of a design point. And that design point should be the operating point in which the machine runs most of the time, because what we do in CFturbo is a best efficiency design for a particular operating point. So for today's webinar, I have chosen that example where a comparably big centrifugal fan has to transport 38,000 cubic meter per hour and had to produce a total pressure difference of 0.265 bar and should run on almost 3,000 revolutions. Of course, the fluid to be conveyed is air, and additionally, there are some inlet conditions that might be used for the CFD export at the end, but those are not necessary for the design because we consider the fluid at that low pressure as being incompressible. Okay, once that is defined, the next step is to add a new component to the project. And I'm going to start with the impeller because that's the one that is the central component of a single stage fan. And if I click on add the radial mixed flow impeller, then the very first design step I have to go through is the definition of the main dimensions. And there are a couple of tabs I have to go through, or I can leave everything as it is by default. So the first tab holds a density value for the solid material. Again, this is not necessary for the aerodynamic design, but if we then later on put some thickness, for instance, onto the hub, we can use that density to calculate the mass of the impeller, for instance. Okay, at the first tab, I can tell whether I want to have an unshrouded or a shrouded fan, whether I want to have splitter or not. Splitters are mostly used by compressors, but of course one can have them also with fans. Sometimes blower manufacturer use them too. The second tab holds a couple of parameters that can be used to get an estimate or a proposal by CFturbo for the main dimensions. And the third tab just holds the actual size of the main dimensions, the actual geometric parameters. So again, these parameters are proposed by CFturbo by just solving 1D balance equations like continuity equation or Euler equation of turbomachinery, plus some empirical correlation. And when it comes to that empirical correlation, some parameters are needed, and they are given at this page. And because one needs to get the correct number of these parameters, there are again functions given, or correlations given, that are implemented in CFturbo, from which one can get these diameters, and very often they are given with respect to the specific speed. And here, for instance, we have the diameter coefficient, which clearly comes from the Cordier diagram, and with a specific speed of 30, which what comes from the design point, we propose a diameter coefficient of roughly 5. And this can be gained for all of the parameters that are given here, and with the help of that, using either the calculate button or the automatic modules, we get these inlet, these main dimensions, and those consist of the inlet diameter, the outlet width, and the outlet or the impeller diameter. And the automatic modus is used if I check that checkbox automatic, then you can see clearly what happens if I change a parameter like the dimensionless impeller diameter, and it clearly shows what happens in the automatic modus. Okay, I want to not go for that automatic modus. I just take these proposals and get rid of this decimal places just by overwriting them, just like that. Okay, once I'm happy, I press OK, and I see in what we call the meridional view, this strange looking meridional contour. The next step allows me to adjust this contour, because here I can give him a certain axial extent. I can tell him what is the diameter of that rounding at the shroud, where is the location of the leading edge, and I can even right-click on the Bezier on that hub curve here, and can tell him you should be a Bezier curve, and there should be a certain curvature and stuff like that. But I want to stick to the simple approach, because very often these fans are made of just metal sheets. And that's why I use the undo feature and go to the initial design. And if I press now, okay, in our meridional view, this looks much more realistic, and we get also something in our 3D preview, in our 3D view. Of course, only hub and shroud have been designed so far, and the meridional location of the leading edge, but this can be clearly seen here in the in that view. The next step is to define the blade angles at leading and trailing edge, and to this end, I use what we call the blade properties design step. Here I can tell him how many number of blades I want to have, and which kind of general blade shape I want to have. And as I said, very often they are quite simple. I'm going to choose the circular 2D blade, which is 2D in axial direction. That's why axial is given here. And with the flow rate or the incidence definition at the leading edge, and the slip definition at the trailing edge, and together with the design point, CFturbo is able to calculate a a proposal again for the blade angles at leading and trailing edge, and those are given here. And because it's a circular 2D blade, it tells you also, because the leading edge position and the trailing edge position in the meridional view is known, it tells you also the blade radius, which is connected to that set of blade angles. Okay, I can from here go directly to the next design step, which is the blade, the mean line design step. And we cannot see any active unity or entity here in that left-hand diagram, because everything concerning that that blade is already fixed because of the circular 2D blade shape. So I could go back and I could change the blade shape to, for instance, freeform 2D. And if I would now go again to the mean line design step, now I could grab one master mean line and could change, for instance, the wrap angle, or could change the distribution of the blade angle just by changing the meridional description of the blade. And then I would have some influence on the shape of that 3D geometry. But because of the circular 2D shape, that was not possible before. So again, I go back to it, switch to circular 2D, and we have the same situation again. Always at the right-hand side in all the design steps, we have a lot of informational values that can be used to make a pre-validation before going into CFD. And amongst them, there are, for instance, that 3D preview, what you already see, or a XY frontal view. And there's even a very simple but fast relative velocity estimate, which can be used in either in order to check whether this estimated relative velocity would somehow meet the accurate criteria. So here, for instance, it touches a bit the accurate criteria, which I would say is fine. But if that would go very deep into that restricted area, then I would say we have to change the blade shape and then the wrap angle and so on. But this is not the case here. Okay, so if I'm happy with that design step, I will also see some change in the 3D model. Now I have a blade with a 0 thickness, and therefore the next design step is to add some thickness on it. In the previous design step, there was an initial thickness defined, which was something like 6 millimeters. Now there is some sort of a polyline with some control points that can be changed, and one can change by changing those control points the thickness at hub and shroud from leading to trailing edge. This is a very simple mode, which is the linear one, but one can also switch to a freeform mode where this thickness distribution now is represented by a Bezier curve. One can do a rounding at leading and trailing edge, and one could even load a thickness distribution from a built-in profile manager, which holds a couple of predefined profiles, such as the NARCA 4-digit profile or the 65 series used in the Lieblein method, point-based data and stuff like that. And of course, this can be extended by the user. Yeah, because again, I want to keep it simple, and also because I want design a fan that can be manufactured just from metal sheets, I stick again to the linear mode, have the thickness constant from leading to trailing edge, and press OK, and then I have a certain thickness added to the mean surface. Now still the leading and trailing edge is sharp, and one would wish to have there a smoother shape, especially at the leading edge. And to this end, there is another design step, which is called the blade edge design step, in which one can say that the leading edge, for instance, should be elliptic with a certain axis ratio, and the trailing edge very often is trimmed with the impeller's diameter. And one can see what that means if I zoom to the outlet and take the trimmed option off. So it's just projected at one side and trimmed at the other side of the blade. Okay, so once I have done that, I'm ready with my initial design of the impeller. And what I also want to do is to add a fans volute. And to this end, I go to the interface and tell add a volute. And the very first design step here again is the definition of the inlet diameter as well as of the inlet width. I keep that as proposed by CFturbo. In the meridional flue, nothing has changed so far, apart from that kind of icon here. And in the 3D view, it's the same, because what we have to define now is what should be the general shape of the volute. So what we have implemented here is quite a big variety of different shapes you can have, and those can also change with the rep angle. The simplest one, again, which I want to use for that fan here, is the rectangular one. That's why I'm going to leave this like that. And the central design step of the volute is this what we call the spiral development area, in which the cross section of the volute are scaled with respect to the rep angle. And there are again some rules implemented, such as the Fleiderer rule or the well-known and established Stepanov rule. And you can change the swirl exponents, for instance, if you go for the Fleiderer's rule. But you can also do a geometric based approach, where you just define, for instance, a final cross section, and then a cross section distribution between rep angle 0 and rep angle 360. I stick to the Fleiderer, and if I look at this in my first initial design, it's looking rather strange, because the inlet width into that spiral is rather small, and that's why, or that gives me the opportunity to say that everything is parametric in CFturbo. So at any time you can go to any parameter, change it, and after clicking OK, you will get the update of the 3D geometry. So now it very much looks different, and it would look like I would expect that. And what I have to add now is just a rectangular outlet diffuser with a certain length. So again, proposals made by CFturbo. I'm going to change the length of that, and keep the end cross section as it is, or maybe I'm going to leave it. And here we are. And the design step to finish that is to add a cutwater on it. And that's really the last design step. And I just go for the simple one, maybe change the angle at which I want to add the, and here we are. Okay, because everything is based on turbo machinery design theory, on 1D balance equation and empirical data, one has to validate this design, and to this end a couple of interfaces are implemented, and one of those is the one that we want to use today. So, and it's called the TCFD interface. There are some things I have to do before I go into that interface, and one is given me here. It tells me that I need a gap between leading and trade between the volute and the impeller, and to this end I go back to it and make an extension, and maybe I just directly connect it like that, or okay. Also, what I need to do is I need to tell that how the 3D geometry is to be generated by the built-in CAD kernel. And if I now save that just on the desktop, for instance, give him a fancy name like test, I can again try. Okay, now I only have some warnings which I can ignore, because here something in the names are just exchanged by some characters. And the only thing I have to do now is to define the STL generation parameters, and I make them all very coarse in order to save some time. And if I do so, I just can export the data and can now give the control file for the TCFD analysis plus the STL data that will be produced to Radek, and he's going to can use that to show the validation of that design in TCFD. Okay, and saying that, I would like to handle the presentation mode back to Lubos.
Okay, thank you, Oliver, for the turbo machinery design part. And now we will move to the simulation part of today's webinar. So before we do that, please let me give a brief description of what is turbo machinery CFD, or TCFD. So TCFD is a unique software developed by Czech company CFD Support. TCFD is a smart, easy to use and affordable CFD software. TCFD was designed for CFD simulations of all rotating machinery such as fans, pumps, compressors, turbines, turbochargers, hydro turbines, etc. It's designed both for radial and axial machines, both for compressible and incompressible fluid flows. The CFD numerical solver is based on OpenFOAM, and we believe the CFD is unique at least for 4 reasons. The number one would be TCFD is always perpetual, which means our clients can keep turbo machinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. And this means that with TCFD, our clients can scale their CFD simulations in a really big way. Number two would be TCFD is fully automated, which means all the workflow from the initial data to the final results, it can be run by a single click or a single command. And all the process is being done automatically. And for this reason, TCFD is extremely effective. Number three would be we deliver the extraordinary technical support, which we are proud of. We keep custom approach to every customer, to every issue. We never leave behind any of our clients' requests. We are very flexible in it, and also technical support is unlimited. So we support our clients even in matters out of turbo machinery field, for example, in numerical mathematics, physics, CFD, IT, or even software engineering. And number four would be the real tutorials are included in TCFD, so the user has no doubts about the best practice settings. There are included the real machines that really exist, and they're already preset. So the user can basically take them, use them, replace the geometry with his own data, and run the simulation. So the start of using turbo machine CFD is pretty smooth. There are many other benefits of using TCFD. I'm not going to go for all of them. I finish here with my last point that TCFD is developed in a way to support the engineers and designers in their real value-added activities. And the beauty of TCFD is that it's the user who decides how deep to dive into CFD or not at all. And all the options remain open at the same time. Okay, so this is just the introduction to TCFD. And now it's time for the live example. So Radek, are you ready for your part of the presentation?
Yeah, hello, yes, I am ready. So can you give me the presentation?
Yes, of course. Here you go.
Okay, show my screen. Okay, thank you. So I hope you see my screen. Okay, so at this point, I will directly start with using TCFD with the connection with CFturbo. So I will start where Oliver ends, or where Oliver ended. So I will open the project which Oliver has just created. So this test project. So I will go directly to the export part. And yes, and here I can export both components, impeller and volute. Here I can set the parameters for the exporting STL. So basically the export contains the STL geometry for each component and the configuration file for TCFD. So here I can set the finest of triangularization of the surface. So usually it's the best to use the finest option to have really smooth and fine geometry. So for this case, I set it here. And now when I would like to directly jump into TCFD after the export from CFturbo, I can check here the open exported file and start exporting. So now it basically making the CFturbo making the triangulation on our design, on our geometry, and in few seconds it will generate all necessary files to run the TCFD. And after export is ended, we can directly work with TCFD. So now the TCFD software is opening, which I have here, yes. So it automatically opens ParaView, in which we have developed the graphical user interface. And as you can see, now we directly can work with the CFturbo design of this centrifugal fan. Okay, so first of all, I will just show you how easy it is to run the simulation to validate your proposed design. So everything is preset. in these menus, I will talk about it later on. You can modify the simulation. So basically now I will just change the number of processors because my computer has not 24 cores, so I will just use 2 for now. But in general, you can use any number you have. Then you click basically here in this pipeline browser, you click the setting item. Then here, this icon of TCFD manager is highlighted. Then you click apply. Here you fill your directory in which the whole simulation will be stored. So for example, my first simulation. Then click apply to prove or to confirm my new name. Then I click the write case. So all necessary files and directory structure is stored and created on the hard drive. And now basically I can run all, which runs the whole workflow of the CFD simulation. So first of all, it creates the computational mesh, then it runs the simulation. At the end, it creates the report, which contain all results or evaluated values, and so on. And this is how this is all the process you need to do to run, to validate your design. So only a few clicks from CFturbo to get the results. Okay, so now I will go into more details. So I will go back. Let's say now I will start from the place where I stored my project. So here I have this webinar. I have prepared this exported geometry. And basically at the beginning, you have these STL files exported from CFturbo and the configuration file. So now I can start by clicking on the configuration file. And now I will show you some setup in more detail. Okay, so first of all, the geometry is loading. Some analysis is running background if the input geometry is okay for TCFD. And after it is loaded, you can nicely see here in the render view. Okay, so back to this menu. So what I can set here, so basically here I can set my setup file. So at any place I can save my current setup and use it anytime later. Of course, you need to set the machine type. So each machine type is specific to run with different solver and different condition and different parameters. So therefore, we have preset some basic turbo machinery designs or machines like fan, compressors, pumps, turbines, hydro turbines, or just stator parts, for example. The next part is the simulation part. Here you can set, for example, if you would like to simulate a steady state simulation or the transient. Of course, the transient is more time demanding and it takes, of course, more time to be simulated, but it is available for more detailed analysis of your design. As I already said, the number of processors is unlimited, so you can choose any number of processor. We perform some parallel performance analysis, and the scalability is quite high. Numerical order first or second. So I will set the first for this webinar example. Okay, the other part, for example, inside physics, you can decide if you would like to simulate as compressible or incompressible. So this centrifugal fan, which has quite, let's say, high compression number, let's say. So we should use the compressible simulation with the Sutherland transport model, for example, with the given parameters. Inside the components, here basically is the setup for the meshing part. So for each component, we set where to find the input STLs, but in general, you can use some external full-length mesh in MSH format, for example. So if you have your own meshing software, so you can import your own mesh here. Then you basically denote what is the input patches, what is the input boundaries, what type it has. It is quite straightforward. So hub is hub, wall is wall, inlet is inlet. Outlet interface stands for the connection between these two components, between the impeller one and the volute one. So each component should be connected by selecting a proper type. Then here are the refinement level, using which you say how fine the mesh should be at the given position. You can enable the boundary layer to be created, and by the last column you define which approach to use for communicating between the rotating part and the non-rotating part. So if the value is higher than 0, then the mixing plane approach is used. I think in CFX it's called for stage. And if you set it to 0, then the AMI approach, or in other words, I think it is said the frozen rotor approach. So I will keep, for example, the mixing plane approach here. And here are some basic parameters of the mesh. So the largest cell size of your mesh, internal point, so which part of your geometry you would like to mesh, so basically inside or outside. So for turbo machinery, or always inside your defined component. And other parameters, here is some topology graph, which is useful when you starting from scratch from your own geometry and you are building the mesh from scratch. Well, the speed lines basically defines how many points you would like to simulate. So each point, let's say, or we can say each point holds the different condition under which your machine is simulated. So here's the rotational speed. Minus is therefore to follow the correct rotation. So it follows the right hand rule. Yeah. So if your time points the axis of rotation, then your fingers shows how the wheel is rotating. So in this way, for this case, maximum number of iteration for each point. Then the turbulence model for K omega SST in this case, but we provide some other turbulence models. The inlet condition. So here I think is the total pressure at the inlet and the flow rate at the outlet. I think, yes. So here I preset more points just to see really the full efficiency map. So I think the design point was something around 11 kilograms per second. Sorry, where are the, yes. Oh yeah, this is the outlet one. Okay, so this is using some special boundary condition developed for the fans. So to automatically create the full efficiency map. Then the initial conditions, so some reasonable initial guess for the flow. Simulation controls include some advanced parameter which is connected to the solver. Post-processing, here you can say from which part of the geometry you would like to evaluate the efficiency. So from what will be the inlet, what will be the outlet, which parts of the geometry should be included into the torque evaluation, and so on. Some automatical visualization can be defined here. So blade-to-blade views, I will show you later on in the report. Some meridional averages you can define here, and you can, for the comparison purposes, you can add some your own graphs which contain, I don't know, for example, a result from measurement or results from another simulation, and so on. Some details about the meshing options. So the automatical meshing, if you don't input your own mesh, is created by the SnappyX mesh. And the scripting is enabled to tailor some option or features which our customers has, so we can directly create a script to follow our customers' needs. Yeah, so basically almost anything can be incorporated into the simulation using these scripting options. Okay, so at the end, if we are fine with our setup, so we can, let's say, click on apply. What I didn't mention is this check setup. So you can click here and it will tell you if every parameter makes sense, what you have said, if everything is consistent with other parameters. So if yes, the case check or this button, check setup button, will tell you if the case is preset okay or not, and what is wrong, for example. Okay, everything is okay, so I can click on settings, can then go for this TCFD manager. I can click on apply, write the case. So yes, second simulation, let's say. Write case, and now I can run the simulation by one click, or I have two options. First, to investigate the mesh. So I can build the mesh component by component or mesh the whole geometry. So I can do it by this. So for example, for now I will click just to see how the volute will be meshed. And just to jump in time, I have prepared, and this is the simulation. Yeah, here. So in this, where is my mesh? Mesh down here. So now I'm at the point where the mesh is generated. So anytime I can visualize each part of my design. Okay, so I can click here into this render view. I can just visualize the mesh. Yes, and here you can investigate how the mesh looks like. And I can add, for example, the rotor part, and investigate if the mesh looks okay. I can perform anything what you want, for example, some slices through your geometry and so on, just to see how the mesh looks like inside. Okay, and when I am satisfied with the mesh, I can simply click run calculation, and the simulation will begin. So always you are informed about the state of the simulation. So I will jump into my, this is the simulation I run a few minutes before this webinar starts. So now the fourth point is simulated. How many iteration is already computed, and what is the overall number of iteration, what time, how long does it take to finish the simulation, and so on. Anytime I can click at the light report button, on the light report button, to see the current state of the simulation. So you can anytime create a light report to see the current state of your simulation, if the residuals are okay. So if the simulation runs as you expected, so you can check it here. And at the end of the simulation, if you should click on the full report, and the full report generates the report which contains all information with all images which are available only at the end of the whole simulation. So graphs of the whole point which you have set for the simulation, and so on and so on. Okay, so you can see here, in this window, you can see what is happening. You can see that the plot of all quantities are now generating, like torque, flow rates, etc. And at the end, the report will appear here. Okay, so just to finish the simulation, so here I have these computed cases which I've run before the simulation. So this is how the case looks like, and the report, the final report, is stored here. So you can anytime open it with your favorite favorite browser, and this is what you get. So just the view of your design, just to see at the first time what you are watching. Then the basic simulation statistics like the setup of your machine, the mesh sizes, the parameters y plus, which is connected to the turbulence model, if it is in the appropriate range. How long does it take to simulate this design, and other stuff. So first bunch of information are connected to the fun characteristic. So this is a special variables defined for fans. So the flow, let's say the compression number with respect to the flow number. So you can see nice graphs and also the values here. Of course, the efficiency. So efficiency for each flow rate. So we can see that the best efficiency point is something, say 11.5 kilograms per second, and it's up to 86%. You can see the convergence of the efficiency, so you can check if there are not big oscillation, let's say, so you can see how the simulation runs. And other parameters like torque, axial force, total pressure difference, total pressure ratio, total pressure per interfaces, and many others. The report is also interactive, so you can see, for example, what is happening between the wheel and the spiral with the total pressure with respect to the given flow rate. So you can really go through and analyze your geometry. Okay, just to finish, at the end of the simulation, you can open, for example, I can go here, you can directly open the case and make your own visualization. So simply if you click this case.foam, then the ParaView with the loaded geometry and loaded results will appear here. So you can apply and make every modification or apply every filters which ParaView provides, like clips, slices, glyph visualizations, streamlines, and so on. Moreover, we have developed our own filters into ParaView, which is the meridional average and the turbo unwrap filter. So this one, which I have prepared in advance, is this meridional average. So you can follow, for example, the total pressure drop along the wheel. Moreover, you can unwrap the wheel into the cubical shape, and then you can make nice slices between the hub and shroud. So this is basically two filters connected together. First one is the unwrap for the hub, shroud, and the blades, on which I have visualized the total pressure contours, as you can see here. And moreover, I make a slice on which I have visualized the relative velocities with the streamlines. So for example, for the given point, you can see if your how the flow pattern looks like. So here you can see that, for example, for this point, there is quite big recirculation at the suction side of your design, and using this information, you can, for example, make some modification in CFturbo design and go for better design, for example. Okay, so I think my time is almost up. So I need to, unfortunately, I have to, I have to hand back the presentation to Luboš. So Luboš, can I give you back the presentation? Are you online?
Yes.
Okay. So I'm giving the presentation back to Luboš.
Yes, absolutely. So thank you, Radek, for your part of the webinar. And now we can move to the latest part of the webinar, which is the Q&A session. So please come up with your questions if you have one or some, and we will answer a few of them and of course all the questions will be answered. So if we can't make all of them, we can answer your questions via email later after this webinar is finished. Okay, so let's have a look what we have, and please come up with your questions. So what we have here, let's take a look. So yes, I can see this. Yep. So Oliver, can you see any question you would like to answer?
Yes, there was, for instance, the question about some comparisons we have made with other design tools, and I can only say that this should not be done by a design tool producer, because he always will speak maybe better for himself than for the others. So yeah, please understand that we have not done that, and it would also not be good if we would do that. So that's one thing, and the other thing is Mr. Brian Bean already left the webinar. Anyway, he asked also how the user is guided to a high efficiency design in CFturbo, and the question is the answer is just as I said before, we use the latest turbo machinery design theory. We use a lot of empirical knowledge that is publicly available and that has been developed by our own and that we ship with the software. And all these is used to really give good initial designs and a good parameterization initially, just in order to get the best efficiency what you can get. So that's what I just can tell in general about that question. Okay.
Okay, Oliver, can you see any other question you would like to answer right now to the audience?
There is, okay, can we import coordinates of turbine blade profiles in the CFD software? Yes, that is possible. At any time in any design step, you can load in any data which somehow can be transformed into ASCII data, and they can be used either as reference, or they can also be used in order to fit Bezier control points in order to get a real good representation of these reference data. So that was Aniruddha Jain's question.
Okay, thank you, Oliver, for answering these questions. Yeah, what else we have? There is a question on whether TCFD can simulate ship hulls with or without rotating propellers, from Mr. Alexander Ursulov. So we can say yes. We have extended TCFD by in the latest version. We have added this simulations of let's say open propellers in an open space. So in TCFD now you can simulate also, for example, wind turbines as well as hull propellers. So it's this. I can yes, I can also give an answer on a question on turbulence models in TCFD to Mr. Sharma, because yes, so basically in TCFD you can use all the turbulence models which are available for standard OpenFOAM. By default, we recommend using K omega SST model. That's what we recommend by default. And yeah, as you know, or as you can learn later, in OpenFOAM there is quite a lot of turbulence models available. So That's a matter of taste and also a little experience of individual users. Okay, I think we are slightly over the time, so I think it's time to conclude now. So as I mentioned, all the answers, all the questions will be answered later via email, so don't worry about it. But now it's time to conclude. So I think this is it from us. It's time to finish. So feel free to contact us. I'm sure you know very well how to do that. The questions about CFturbo are to be sent to CFturbo company. The questions about TCFD are to be sent to CFD support. We will gladly support you in your projects, so feel free to contact us. It's our job and also a pleasure. And yeah, so anything more to say, Oliver?
The only thing I would say is that I thank all of the audience to take the time and join the webinar. Thank you, and hope that we get in touch somehow.
Okay, thank you. Radek, would you say anything more?
Well, basically, I will say the same. So thank you very much for watching us. And if you have any question or any comments, or if you would like to discuss something, so do not hesitate to contact us. Contact us at CFD support or contact Oliver at CFturbo. And yeah, have a nice rest of the day. Bye.
Bye-bye.
Okay, all right then. So we leave you with that. So thank you for your attention. We are looking forward to collaborating with you. Stay tuned and bye-bye for now.